every time you send a message, watch a video, or you make a payment online. These are the day-to-day activities we do. But have you ever thought how your data is reaching safely to the servers? There is a one protocol silently working behind the scenes to make sure that nothing goes wrong. The protocol is TCP. Understanding that TCP is important in the networking and also in cybersecurity. This video is going to be quite lengthy because we are going to cover each and every concept involved in the TCP. Trust me, by the end of this video, you will become a master in TCP. Once you understand the TCP, network will become much easier for you, and it will also help you to troubleshoot network issues more effectively. Okay, so let's take simple example and understand how TCP works. This is a general example. Imagine you are attending a job interview. Okay, first you walk in and introduce yourself to the interviewer. The same way we do three-way handshake in the TCP. Then you carefully deliver everything you know to the interviewer. Okay, so that the data exchange happens in the TCP. And finally, once it's over, you politely say goodbye and leave. That's the graceful termination which we do in the TCP by using four-way handshake. Believe it or not, this is exactly how TCP works. Okay, now let's look at the today's agenda. First, we will see the introduction to TCP. Then we will cover TCP Header details. And after that, we will see connection establishment using three-way handshake. Next, we will look at data transmission using segments, reassemble and TCP timers. Once the data transmission is completed, we will cover flow control and congestion control. These two concepts are very important in the TCP. After that, finally we will see the connection termination. How gracefully we will terminate the connection by using four-way handshake. So these concepts cover everything about TCP. Once you understand them, you will become a master in TCP. So without wasting any more time, let's step into the TCP world, understand the importance of the TCP. Let's understand why we need TCP. If you remember in the OSI model and TCP protocol suite, where I explained all the layers, let's quickly recap what we discussed. At the physical layer, the data is just raw bits moving across wires or wireless signals. Then the data moved to the data link layer. What we have done? So we grouped the bits into the frames and we added the MAC address. Then we moved to the network layer. We used IP address to find a best path from source to the destination. So far, all these layers, what we have done, everything we packed it and we are ready to go to the destination. But here the question, we should get it that what if the data gets lost on the way? What if the data gets corrupted? And also if it arrives out of order? So we need a reliable transport mechanism, right? To make sure your data is safe, complete and in the correct order. That's why we call it as the transport layer. In the transport layer, we have two protocols. The first one is TCP and second one is UDP. For reliable protocol, we use TCP. For better understanding, let's take a general example how TCP works. Imagine you are ordering a mobile from the Amazon. So once you order, the Amazon pack your order and give it to the delivery boy, right? So now imagine if there was no proper delivery procedure here, your mobile gets lost or stolen or you will deliver to the wrong person. This is completely risky, right? Instead, they follow the proper process. The delivery boy brings the mobile and give it to you. Once you receive it, you sign or acknowledge you got the phone safely. This is exactly how TCP works. It's deliver your data reliable from source to the destination. It's ensure that nothing is lost or corrupted and requires the acknowledgement to confirm successful delivery. Okay, now we understand why we need the TCP. Let's look at the definition of the TCP. TCP stands for transmission control protocol. It is one of the important protocol of the internet. It works at the transport layer of the OSI and TCP IP models. It is responsible for making sure that data is delivered reliably, in order and without errors between the two devices. So that's important TCP is. If you look at, many protocols are used TCP for reliable communication. If you want to try to access any website, after DNS resolution, the next protocol we use TCP for reliable communication. Not only HTTP, there are many protocols use TCP for reliable communication. Okay. Now let's look at the key characters of the TCP. Okay. The first one is connection oriented. What does it mean? We all know that TCP follow the three-way handshake to establish a reliable session between sender and receiver before sending any data. Okay. So this one of the key character. We'll discuss more about the three-way handshake. Okay. The second one is reliability. How do we make sure that the communication is reliable? Its guarantees delivered by using sequence number and acknowledgements, including retransmission if necessary if any packet get lost. Okay. So this is also one of the important characteristics of the TCP. So the third one is ordered delivery. It will reassemble the data in the correct order if the packet arrives out of sequence. Okay. So the next one is error detection. How do we find the errors? We use checksums to detect the corrupted data. So if we find any corrupted data, we will retransmit the data to the receiver. The next one is flow control. So this is important function in the TCP. It ensures that sender does not overwhelm the receiver by sending too much data. Okay. And final one is congestion control. It prevents the network congestion by adjusting sending rate at the network level. Okay. So these are the key characteristics of the TCP. I know that you might not fully understand these characters. This is quite common. Even I faced the same issue when I was studying the first time TCP. So first you understand the characters, but you won't fully get them. Then you need to study the TCP header, concepts like flow control and congestion control. Once you finish those concepts, then revisit the key characters. You will completely understand each and every characters of the TCP. Okay. So as we discussed, now we'll see the TCP header. Before we move into the TCP header details, let's understand every protocol has a header. If you have observed, have you ever asked yourself, why do we actually need headers? The reason is very simple: identification and control. So this header tells us who is the source, who is the destination, what to do with the data, where to send it, and how to process it. All this important information embedded in the header. So every protocol looks like a header plus data. So the data you are sending is stored in the data field, while the header contains the protocol specific details needed for communication. Okay. Let's take funny and simple example. We can all relate it to this example for understanding why we need the headers. Okay. The example is goods train. When you look at the goods train, the front section is the engine and the driver coach does all the hard work. It knows the route and controls the speed, ensure that goods reach to the right destination. So the rest of the train just follows. In the same way, the protocol header works. Now let's look at the TCP header details and carefully understand each field one by one. Before we jump into the TCP header fields, let's understand the TCP header size. The TCP header has a minimum size of the 20 bytes and the maximum we can extend to 60 bytes, which we use for the TCP header. Okay. Now let's discuss one by one each field in the TCP header. The first one is source port. What is source port here? The source ports identify the sending application. Okay, let's imagine you are trying to access a website. Your computer will use a random port number such as 49532 or 3657. This is a source port which is a random port number. Okay, so it depends on the application, it takes the random port number. Okay, the next one is destination port. The destination port identifies the receiving application port number. We know that each protocol uses specific port numbers. For example, if you are trying to access a website, the destination will be port 80 for HTTP or 443 for HTTPS. So, this source and destination ports together ensure that packet is delivered to the correct application at the both ends. The source port would be random port number assigned to the sending application. Destination port is a well-known port number is assigned to the receiving application like 80, 443, 21, 22, etc. So, this is all about the source port and destination ports fields in the TCP header. Okay. Now, let's move to the another field, that is sequence number. Where do we use sequence number? Why we use sequence number? If you remember in the OSI model, I explained the segmentation at the transport layer. I told you that the large data split into small pieces we called as a segments at the transport layer. Each of the segment is assigned to a sequence number. The reason we assign the sequence number is to track the order of the data while it's being sent. So, this sequence number helps to receiver reassemble the segments correctly in the original order. That's why we use sequence number exist in the TCP header. Okay. Now we understand the what is sequence number. Why do we need it? Then we need to move to the next one, that is acknowledgement number. So this field is used by the receiver to tell the sender, hey, I got your data up to this point, now send me the next segment. Basically, we are acknowledging the data that is sent by the sender. We added the sequence number and we send to the receiver. Now receiver received the data and is acknowledging the data that is sent by the sender. So as we discussed, the sender is divided the data segments and assigned the sequence number to each segments. This acknowledgement confirms the segments have been received successfully. So this is how TCP make communication reliable, ensure that no data is lost or corrupted by using sequence number and acknowledgement number. So next move to the another field, that is data offset. It is also called header length. So as we discussed, TCP itself header has a own length. The minimum length is 20 bytes and the maximum length can be 60 bytes. So this data offset field tells the receiver how long the TCP header is, which means the receiver knows that where the header ends and the actual data begins. So those information will be stored in the data offset field. Okay. So the next one is RSV. This is something for reserved. Okay. So currently this field is always set to be 0. This is something for future purpose. Okay. Now we move to the important field, that is TCP flags. This is also one of the interview question. Okay. So there are different flags in the TCP we do have. Let's discuss one by one. First, let's understand what is TCP flags. They are tiny, just 1 bit each. They control the entire state machine of the TCP communication connection setup. They control flow control and more. Okay. So let's understand each flag one by one. Okay. The first one is synchronization. Why we use synchronization? It is used to initiate a TCP connection. So basically, if you want to connect any server, this flag is set to be 1. The client sends the synchronization packet to the server to begin the process. Without the syn flag, you can't even start connecting to the server. So in simple terms, if we can say, this flag is used to initiate the connection. Okay. The next one is acknowledgement. So this flag confirms that the data has been received. So it is always used after the connection is established. In fact, every TCP packet after the handshake has the acknowledgement flag set to be 1. The reason is after three-way handshake, the data will be exchanged. So we need to acknowledge the data to the sender and receiver. It is also carries the acknowledgement number telling the sender, hey, I got your data up to this byte, now send me the next one. So this is what makes the TCP is reliable, and we are also constantly acknowledging the data sent by the sender. Okay, so this is all about the acknowledgement flag. Now move to the finish flag. Let's imagine once your data transmission is complete, we need to terminate the connection. So that time we use finish flag to gracefully terminate a connection. When one side is done sending the data, it sends finish packet. The other side acknowledge with the acknowledgement packet, and it usually sends the own finish packet. So this is a part of TCP four-way termination process. We'll talk more about later in this video. Okay. For now, just understand that this flag is used to terminate the session gracefully. Basically saying that I am done talking, you can close after acknowledging. Okay. So that is all about the finish flag. Then move to the reset flag. Where do we use? When do we use? So this flag is used to immediately terminate a connection. For example, if a packet arrives at a port number which there is no services on listening, or if a connection becomes invalid or corrupted, so that then reset packet will be sent. Unlike proper handshake or terminate the sequence, it's a reset like a sudden disconnection. Just understanding that you are talking to your friend and all of a sudden you are hanging up the phone without saying goodbye. So that's exactly this reset packet works. Okay. The next one is push flag. This flag tells the receiver to deliver the data application immediately without waiting for the buffer to fill. Normally, TCP can buffer data, deliver it once it has the large chunk. But if the push flag is set to 1, it means the data should be sent and delivered right away without waiting. For better understanding, let's take a real example. You open your browser and your browser requests a web page. Now the TCP segment carrying the HTTP data often have the push flag set. Why? Because web traffic is interactive. So the server wants your browser to process the data immediately like HTML, CSS or email image instead of buffering and waiting. That's where we push flag comes into the picture. Okay. So now let's move to the another flag, that is urgent flag. This urgent flag is little different. So where do we use this urgent flag? So when the flag is set to 1, it tells the receiver that part of the data in the segment which is urgent should be prioritized. Along with the urgent flag, TCP also uses the urgent pointer field, that is a different field in the TCP header, indicate that where the urgent data ends. We'll talk more about when we reach the urgent point field. Now you should understand is where do we use this urgent flag? In real time, imagine you are downloading a file over a telnet and suddenly you wanted to stop the downloading. What do? You press Ctrl C. So once you press the Ctrl C, we call that is a interrupt signal. So this interrupt signal marked as a urgent and sent using urgent flag. So the receiver process it immediately, keeping a normal data aside. Okay, so this is all about the urgent flag. So many people get confused between the push flag and urgent flag. But here the key difference. Push, it's delivered all the data immediately without waiting for the buffer to fill. Urgent marks a portion of the data is urgent, so the receiver process it first and before the rest. Okay, and there are advanced flags like ECE, CWR, NS. So these flags are used for TCP congestion control. They are not normal connection setup or connection termination like SYN, FIN or reset. So this is something we should cover under the congestion control topic. So before we understand these flags, we first need to understand what is congestion control is. Once we cover that, we'll talk more about these flags in the detail in the congestion control. Just remember, now these flags are specially used for congestion control and congestion management. Okay, this is all about the TCP fields. Now let's move to the next important field, that is window size. This is actually very common interview question, so make sure that you understand it well. What is window size? Why do we use the window size? The window size field in the TCP header, it is mainly used for flow control. So what does it do? It tells the sender how much data the receiver can accept at the moment. If we put in simple words, it tells how much empty space is available in the receiver buffer. Okay, think of like a bottle. If the bottle is almost full, the receiver says, hey, slow down, my window is small now. Once the bottle is empty again, the receiver says, go ahead, my window is large, now you can send the more data. So window size is essentially the advertise the range by the receiver, so to control of the flow of the data. Okay, now you may have a question. How is the window size calculated? Typically, it is related to the receiver buffer space in the RAM that managed by the operating system network stack. Your laptop OS decides how much data it can handle at once and inform the sender via the window size field in the TCP. Okay, so this is all about the window size. It's control the flow between the sender and receiver advertising the window size. Okay, but here the one more concept we should study, that is calculated window size. This is not an official TCP header field, but you can only see it in tools like a Wireshark. Let's understand the calculated window size. Typically, the TCP window size field in the header, it's only 16 bits. Okay, so this means maximum value it can represent 65535, which means 64 KB. This was found in the earlier days of TCP, but as network got faster, 64 KB buffer space was not enough. So to solve this limitation, they introduced window scale option during the three-way handshake. So this scaling factor can be 0 to 14. This allows the window size to be multiplied by 2 power 14. Okay. Now let's take one example and understand how calculated window size works. We all know that the window size is default 65535. We know that we use window scale in the three-way handshake for increasing the window size. Let's say if the scale is 2 power 2. Okay. Now you can calculate 65535 into 2 power 2. We'll get some number here, right? So this means this buffer space is much larger than raw 16-bit field allows. So we are increasing the buffer space in the sender and receiver by calculating the window size. Okay, so remember, window size field is an official TCP header field that is 16-bit, which means 65535 64 KB, which is the default one. So they introduced concept called window scale option. So this is can be negotiated during the three-way handshake. Okay, so now we can calculate the window size is 16-bit of the 65535 into multiply window scale. You can take 0 to 14 value. You can multiply into 16 bits, which means 65535. You will get a random number. So this way, this is the way like you can improve the window size. Okay, so this is all about the window size. This is very important to understand. Okay, now let's move to the next field, that is TCP checksum. Why do we use TCP checksum? This checksum is used for error detection in the TCP. So it ensures that both your data and header haven't been corrupted during transmission. So basically it is for error detection. Okay, how TCP checksum works? We all know that every TCP segment have payload plus header. Now we need to calculate the checksum value. How do we calculate? We use one's complement method. After calculation, we will get a value. So that value will be placed in the checksum. Okay. So when the receiver gets the segment, it recalculates the checksum to an arrival. If the recalculated checksum matches the value in the header, the segment is considered as a valid. If it does not match, the segment is discarded. Will ask the sender to retransmit the packet since it is corrupted. So in short, the checksum is for error detection. Both the sender and receiver use one's complement addition of the header plus data. Will get then a result. If the result match, which means there is no error. If the results do not match, the segment is corrupted and must be retransmitted. Okay, so this is all about the checksum. Now let's move to the TCP urgent pointer field. Basically, it is used in the combination with the urgent flag as we discussed earlier when we talk about urgent flag. So this urgent flag indicates that segment contains urgent data, so the receiver should prioritize it immediately. Now, how does the urgent pointer work with the urgent flag? So the sender set the urgent flag equal to 1. The urgent pointer fields contain the offset from the current sequence number to indicate that where the urgent data ends. So this marks urgent portion of the data. So when the receiver sees the urgent flag, it processes of the urgent data first before handling the normal data in the buffer. Okay. Let's take same example which we took in the urgent flag. Imagine you are downloading a file over a SSH or telnet. Suddenly you press Ctrl+C to interrupt the downloads. So for Ctrl+C, we treat them as an interrupt signal. So this interrupt signal is sent as a urgent data. This urgent pointer tells the receiver to handle the signal immediately rather than waiting for the rest of the normal data. Okay. So this is how this urgent pointer works. If we put in simple term, this urgent flag is used to mark the prioritize the data, and the urgent pointer tells the receiver where the urgent data ends. Okay. This is all about the urgent pointer. Okay. Now let's move to the last field, that is options. Why do we have options field? So basically it is used to provide the extra features or capabilities that are not included in the standard TCP header. What are the common TCP options we have? The first one is MSS. The second one is selective acknowledgement, and third one is time stamp. Okay. So these are the common TCP option which we see in the option field. Let's discuss one by one. What is MSS? MSS stands for maximum segment size. So as we discussed in the transport layer, TCP breaks the data into segments. Okay. So but we need to understand what is the largest segment size which we can handle. So basically this option tells the other side that largest segment size it can handle. It ensures that segments are not too large to avoid fragmentation. It tells the largest segment size it can handle. Okay. So that's why we use maximum segment size. Okay. The next one is selective acknowledgement. Where do we use selective acknowledgement? So basically selective acknowledgement allows the receiver to say, let's imagine the sender sent 10 packets to the receiver. Now the receiver to say, I got packets from 1 to 5 and 7 to 10, but packet 6 is missing. Now the sender only retransmit the missing packet, okay, which is allows the fast recovery less wasted bandwidth instead of sending all the packets. If there is no selective acknowledgement, so if the one packet is lost, everything is after it must be resent. This is how like the selective acknowledgement will be used. Okay. The next one is timestamp. So the name indicating itself, which is used to measure round trip time and prevent all duplicate packets. How does it work? While sender sending a data, he will add a timestamp when sending packet. Now receiver receives the data and it send it back in the acknowledgement packet. Now sender can calculate round trip time. How does it calculate? The current time minus original timestamp. So this helps TCP knows how long it takes for a packet to go and come back. Okay. So this is all about the complete TCP header details in depth. Okay. Now we understand that why we need TCP and what fields exist in the TCP header. Now we are ready to establish a connection to the server. Okay. We'll take one example and try to understand how the connection happened between the client and the server. Okay. So before sending any data, TCP needs to establish a reliable connection between the client and the server. As we discussed, TCP uses a three-way handshake to connect to the server. Let's see how the connection establishment works. Okay. The first, client sends the synchronization packet. If the client wants to start a connection, it sends the synchronization packet to the server. Okay. If you remember in the TCP flags, we discussed about one flag which is used to initiate a connection. Yes, the SYN flag is set to be 1 since we are initiating the connection here. Think like this. Hi server, I wanted to connect you. Here's my starting point. Okay. Once the server receives the SYN request, it responds with a segment where both synchronization equal to 1 and acknowledgement equal to 1 in the TCP flag. This means, hi client, I am ready. I acknowledge your request. Here is my starting point. Now the client receives the SYN from the server. It sends back segment with the acknowledgement equal to 1. It's confirming it, receive the server response. Now the connection is established. If we put in simple way, first client send the synchronization packet to initiate a connection. Then server sends the SYN, acknowledges and synchronizes. Then client send the acknowledge. So acknowledge the server. After this, the TCP's connection is fully established and that data can be transmitted reliably. Okay. For better understanding this, let's analyze the TCP packet in CloudShark. Okay, let me zoom in. Yes, this is the TCP protocol. Here you can see that source port is the random number. As we discussed, the source port could be random number. The destination port is 80. Since we are trying to access a web server, by default it's taken a 80 port number. Okay. So whatever we are seeing this in the bracket, which is added by the server, which is added by the Wireshark. Okay. Here you can see the sequence number and here you can see the acknowledgement number. Okay. So here we do have the flags. See, since it is the synchronization packet, the SYN flag set to be 1. Okay. Here you can see the window size, how much data you can receive at this time. Okay. So here you can see the calculated window size and also you will see the checksum for error detection. And here you can see the urgent pointer is 0 since there is no data to be urgent. And here you can see the options. This is MSS and selective acknowledgement permitted and you can see the timestamps here. Okay. So this is all about TCP header fields which you already discussed. Now coming to the three-way handshake. Here you can see the three-way handshake. Here the first client sends the synchronization packet, then server sent the synchronization plus acknowledgement. Then client sent the acknowledgement. So this is how the connection is establishment. Here I wanted to highlight one more topic here, how the sequence number and acknowledgement works. Let's discuss here. See, the sequence number is, it will be taken by the random number. It's taken here 1000. Okay. So first synchronization packet, the acknowledgement will be the 0. Okay. The flag is the SYN. Now the client is initiating the connection. Okay. So once the server receives a response, it will take the random sequence number. Here it's taken by the 5000. Okay. Now the server is acknowledging with the sequence number sent by the client, that is 1001 SYN. So server acknowledge plus SYN. If you see here, client and server. So server acknowledge the 1001. So we are not touching the 1001 here. We are acknowledging the server number, that is 5001. Okay. So this is how like the sequence number and acknowledgement works. Okay. So now that we have completed the handshake successfully and established a connection with the server. Now it's time for data transmission. Okay. Once the three-way handshake is done, how does the data transmission happen at the TCP level? Okay. What are the key functions in the TCP data transmission? Okay. Let's discuss one by one. The first one is segmentation and reassignment. Okay. So now we received the data from the application in the large chunks. But all we know that the network cannot send all the data once because maximum transmission unit limits. What is maximum transmission unit here? Why do we use MTU? M2 is a actual size of the packet, which including headers that can be transmitted over a network. This MTU is defined at the IP layer. So once we receive the data from the IP layer, we will check the MTU size. Okay. So once MTU size is fixed in the IP, so TCP must ensure that each segment fits within the MTU. That's why we segment the data. So once the data is segmented, each segment is assigned a sequence number as we discussed earlier. And also we need to understand maximum segment size here. So MSS define the largest TCP segment that can be fit into the MTU size. Okay. A lot of people get confused between the MTU and MSS. MTU equal maximum packet size allowed in the link, which including the headers. Okay. MSS, maximum TCP payload, only the data part inside the packets. So this MSS make sure that that is fit into the MTU, which is fixed in the IP. Okay. So segment is all about the splitting the large sinks into smaller TCP segments, assigning the sequence number, ensure that each segment fits within the MTU. Okay. So once the receiver receives the data, he sends back the acknowledge to the sender. So this acknowledgement indicates, hey, I have successfully received all the data up to this point. Please send me the next one. So this is how ensure the reliable communication happen. Okay, that is used by segmentation and reassemble. Okay, so now to achieve this reliable communication, we need to understand TCP timers also. Okay, let's understand why we need the TCP timers. We all know that sender waits for acknowledgement from the receiver. What if we don't get acknowledgement from the receiver? Will we wait forever? No, right? We all know that our networks are not always perfect, or there can be packet lost, delayed, duplicated, or arriving out of order. So these particular TCP timers make sure that data does not get stuck, and also if required transmit the packet. Okay. So these particular TCP timers make sure that the data does not get stuck, and also if required retransmit the packet. Make sure that the connection stays reliable. That's why we use TCP timers. Okay. There are different TCP timers we do have. Let's discuss each timer one by one. Each timer has different purpose. Okay. The first one is retransmission timer, which is also called retransmission timeout. So when do we use the retransmission timeout? Let's imagine when a sender send a packet. Okay, obviously he wait for acknowledgement from the receiver, right? But sometimes packets are lost, delayed, or dropped in network for many reasons. So what is this transmitter time do here? As soon as the sender transmits the packet to the receiver, it starts a timer. Okay, if the sender does not get an acknowledgement before this time expires, it assumes that packet was lost, then I need to retransmit the packet again. Okay, so this is how retransmission works. It ensures that the data is not lost even in unreliable network. Okay, so this is all about the retransmission timer. Okay, now let's move to the next one, that is persistence timer. What is persistence timer? Why do we use? Sometimes we know that receiver buffers become a full. In that case, receiver tells the sender, my window size is 0. Don't send me any more data right now. If you remember, the window size is used for the flow control. It will advertise the window size and how much data received at that moment. If the window size is 0, which means he cannot receive the data. Okay, so here the problem. How does the sender know when the receiver window size become a greater than 0 again? Okay, he got a response that window size is a 0. But how does he know that receiver window size become a greater than 0? If nothing is done, sender might end up waiting forever, never sending data again. Okay, to prevent this, the persistent timer come into the play. So when the window size is 0, the sender starts a timer. Okay, so once it is expires, the sender sends a probe packet. Probe packet means like which is very small or even empty packet to the receiver. Okay, the probe packet is basically asking, can I send now? When the receiver responds with the updated window size, then the senders know that whether it can continue sending data. So this is how the persistent time ensure communication does not get stuck when the window size become 0. Okay, so this is all about the persistent timer. Now let's move to the another timer, that is keep alive timer. Where do we use this keep alive timer? Sometimes a TCP connection may stay idle for long time without doing anything. The connection is active but you are not doing anything. In such cases, the sender cannot know if the other side still alive or if the connection has already terminated. That's where the keep alive timer helps. After a certain ideal time, this timer makes the sender transmit small probe packet to the receiver. If the receiver responds, we can confirm that the connection is still alive. If there is no response after sending several probe packets, the connection will be closed. So this is how keep alive timer help to detect dead or inactive connections. Okay. Now move to the another type, which is time wait timer. This is used to gracefully terminate the connection. When do we use it? After a TCP connection is closed, it does not end up immediately. Instead, it goes into the special state called time wait. Okay. So this time wait state exists to handle any delayed packets from the closed connection that might still moving on the network. So the time wait timer makes sure that old packet that don't get mixed with the new connection. Okay, it will be considered as a security breach if it mixed with the new connection. Okay, it is also ensure that all the data is completely received. So for that, it will wait for some time and make sure that receive the complete data. Okay, we'll talk more about this in the TCP 4-way handshake. How do we gracefully terminate the connection? But particular this timer which we used in the 4-way handshake. Okay, now move to the final one, that is delayed acknowledgement timer. So when do we use this? We all know that sending an acknowledgement packet for every small packet that can be waste bandwidth, right? So what the TCP delay acknowledgement timer do here? Instead of immediately sending the acknowledgement for each segment, it will wait for short time like around 200 milliseconds. If the another segment arrives during that time, what the TCP timer will do? TCP send a single acknowledgement for both packets. This way, it saves the bandwidth while still keeping the communication reliable. Okay, so this is all about the TCP timers. By using the TCP timers, we make sure that the communication should be reliable. Okay, so far we have covered the how the data is divided into small segments and how we are assigning the sequence numbers for the segments, and also we acknowledge for the reliable communication, and also saw how the different TCP timers works to maintain the reliability. Now let's think about this. We all know that the data should travel across the network to reach the servers, and we should also consider how the sender and receiver handle the data. To manage this properly, TCP introduced two important concepts, that are flow control and congestion control. How do we make sure that the flow of the data is controlled and congestion is also managed? That's what we will discuss next. Okay, first let's understand what is flow control. What is flow control and why do we need it? Okay, we all know that each system has a different capacity to handle incoming data. So we must ensure that we are not sending too much data at once to the receiver. So this prevents the sender from overwhelming the receiver. Okay, to maintain this, to achieve this, TCP uses two concepts, that is window size and the second one is sliding window. We already covered the window size in the TCP header, but let's quickly recap. It allows the receiver to tell the sender how much buffer space it has by advertising the window size in the TCP header, which means the sender can only send the data, that much data at that time. Okay, so by seeing the number, the sender does not need to wait for acknowledgement immediately. They can send the data. But when sender waits for acknowledgement, when the receiver buffer is full, it will advertise the window size of the 0, which means the signaling the sender to stop sending data until my space is available. So this is how window size works. Now let's focus on sliding window. What is sliding window and when do we use sliding window? The sliding window is a dynamic allowance that tells the sender how much data it can send before waiting for an acknowledgement. Okay, once the receiver processes some data, the particular slides the window forward, allowing the sender to transmit the data. I know that it's a bit confusing. Let's take simple example and try to understand. For example, suppose the receiver buffer is 10 KB. It advertised the window size is 10 KB. Now the sender is send the data 10 KB. So now the receiver process the 5 KB and also send the acknowledgement with the new window size of the 5 KB. So the window slides forward, allowing the sender to send the next 5 KB. So whatever the receiver is updating his window size, where the window size is forward, allowing the sender to send the next data. So it makes sure that sender can keep transferring the data without waiting unnecessarily, maintaining efficient of flow control. If we put in simple terms, the receiver advertises its window size, how much data it can accept. So the sliding window adjusts the size once the receiver processes the data. So making sure that sender does not wait unnecessarily and also have updated the window size. So this is how flow control works. Now we will discuss about the congestion control. Before moving to the congestion control, let's understand the difference between the flow control and congestion control. A lot of people get confused here. Flow control happens between the sender and receiver, while congestion control happens at the network level. Okay, now let's understand what is congestion control is. Congestion control is a mechanism in the TCP to prevent too much data from being sent into the network at once. Okay, which could overwhelm the routers, switches or other network devices. It can be causing the packet loss, delays or degraded performance. We all know that network levels have their own limited bandwidth. If many devices send a large amount of the data simultaneously, packets get dropped. As I mentioned in the TCP header, we will talk about EC and CWR flags in the congestion control topic. So now we need to discuss about these two flags. So basically, ECN flag represents the collaboration between the IP layer and TCP layer. Okay, how does ECN works? ECN stands for explicit congestion notification. So typically, TCP detects congestion only after packets are lost, but ECN allows the network to notify the sender before any packets are lost. Okay, so how does it work? What is the flow? So when there is a network detects the congestion, router marks the packet in the IP header to indicate that this particular network is busy. So when the TCP layer sees the packet, so the ECE flag set to be 1. So it tells the sender there is a network congestion, you should slow down. So basically it indicates that there is a congestion at the network level. So when receiver receives the packet, the IP header shows this, meaning there is a network congestion. So this ensures that sender slow down before any packet loss occurring by the set ECN flag 1. So this is how ECN works. Now let's discuss about CWR flag. So the CWR flag stands for congestion window reduced. It is used by the sender to acknowledge that I have received the ECN notification and also slow down the sending rate. So the sender set the CWR flag to 1 in the next packet, inform the receiver I has reduced the congestion window. Basically it is an acknowledgement from the sender, it has reduced the congestion window. So this is how congestion is controlled using these two flags in the TCP. Is this enough to control the congestion? No. To prevent this, TCP also uses different algorithms in the congestion control. Let's discuss one by one. The first algorithm is slow start. The purpose of this algorithm is to avoid overwhelming the network when starting a new connection. If you start a new connection, this algorithm to avoid the overwhelming the network. How does it work? So initially, TCP starts by sending the small amount of data instead of sending too much data at the network level. Okay. So every time if you get an acknowledgement, the congestion window doubles. You may have a question here. What is congestion window? Congestion window means how much data the network can handle without congestion. Okay. So this continues until it hits threshold called slow start threshold. What is slow start threshold here? Slow start threshold is like a speed limit sign. It was below TCP speed up quickly. Once it hits the sign, it slows down the speed. So in simple term, what is slow start algorithm means? We start by sending small amount of data with each acknowledgement the congestion window doubles until it reaches the slow start threshold. So this is how TCP avoids overwhelming the network when starting a new connection. Okay. Now next move to the next algorithm, that is congestion avoidance. Where do we use? What is the purpose? The purpose of this algorithm is carefully increase the data rate without causing the congestion. So once the congestion window reaches the slow start threshold, as we discussed in previous algorithm, so the TCP stops doubling it, instead increasing the window slowly. So we slow down the data rate to avoid congestion at the network level. This is how TCP perform the congestion avoidance. Okay. The next one is fast retransmission algorithm. What is fast retransmission algorithm? What is the purpose? The purpose of the algorithm is to quickly recover a lost packet without waiting for the retransmission timer to expire. If you remember, we talked about the retransmission timer in the TCP timers. Let's imagine if the sender keeps receiving the duplicate acknowledgements from the receiver for the same packet. It assumes that the packet might get lost. Okay. So the sender retransmits the missing packet immediately instead of waiting for the retransmission time to expire. So this is how fast retransmission works. Okay. We move to the last one, that is fast recovery. So where do we use? This is used for avoiding the reducing the congestion window too much after a packet loss. So how does it work? So typically if we see any packet loss, it reduces the congestion window. Okay, let's imagine after a fast retransmitter, the last packet is successfully retransmitted. So the TCP reduced the congestion window by half instead of going back to the one maximum segment size. What is MSS here? The TCP can only send one segment maximum size before waiting for an acknowledgement. It is very slow. Okay, so instead of going back to the one maximum size, the TCP reduces the congestion window by half. So this is how fast recovery works. So this is all about the core congestion control algorithm used to prevent network congestion. Now we have done everything. We established a connection. We managed data transmission by segmenting the data, assigning the sequence number, sending acknowledgements, and used TCP timers. We also handled how flow control happens and how congestion control happens. Now the next step is terminate the connection gracefully. How do we do that? If the client wants to close the connection, how do we close the connection gracefully? As we discussed, TCP follows four-way handshake to completely close the connection, ensuring that both sides to agree to terminate the connection gracefully. So it follows the four-way handshake. Let's discuss one by one. Here the first step. The client sends a FIN packet to the server. As soon as the client sends the FIN packet, it moves to the state FIN wait 1. What states here? The state represents how both sides move step by step to close the session gracefully. Okay. So now the step 2 is the server receives the FIN packet from the client and is sent back acknowledgement to the client. As soon as the server sent acknowledgement to the client, it goes into the close wait state, which means the server may still send the remaining data before it closes the connection. Okay. So now the client receives the acknowledgement from its own FIN, what he sent. It moves from FIN wait 1 state to FIN wait 2. So now the client is waiting for server FIN flag. Okay. Step 3. Once the server finishes sending all the remaining data, it sends the FIN flag to the client. As soon as the server sends the FIN packet to the client, the server now moves to the last acknowledgement state. So it waiting for the final acknowledgement from the client. Okay. The step 4 is the client receives the server FIN and send back an acknowledgement. Okay. So the client now enters into the time wait state for 2 into MSL to ensure any delayed packets are handled. What is MSL here? MSL equal to maximum segment life. What does it mean? It is the maximum time TCP segment can live in the network before being discarded. So we have mentioned 2 MSL, right? So 2 times MSL means the connection stays time wait for double the MSL. So 1 MSL to wait for any delayed segment, another MSL to handle the possible retransmission. For example, if the MSL 30 seconds, then the time wait lasts 60 seconds. If the MSL 60 seconds, the time wait lasts 120 seconds is almost 2 minutes. Okay. So after that time wait timer expires, the client moves to the closed state. Okay. So the server after receiving the final acknowledgement also moved to the closed state. This is how TCP gracefully close the connection from both ends. So this is all about the complete TCP. I hope it gave you a clear idea about TCP. If you really like this video, please like, share and subscribe to my channel. We'll meet in the next with another exciting protocol. Until then, take care. Bye bye.